Hey guys, today's video is going to focus on vapor pressure. We're also going to talk about vaporization in general. We'll get into a discussion on boiling point and ultimately end with a quick look at the significance of intermolecular forces. All right, so to start off, when molecules are in the liquid state and they have sufficient energy to escape the surface of that liquid, if they're in some confined container, we know that a phase change will occur. Okay, we will transition from the liquid to the gaseous state, and that's what evaporation or vaporization is, right? It's this process of going from the liquid to the gaseous state. We also know that as we increase the temperature, we increase the kinetic energy. Okay. Now, as we increase the kinetic energy, we're giving this energy to the molecules themselves. And that energy is being used to overcome the intermolecular forces that exist between one molecule and its neighboring molecules. Again, these aren't bonds. These are intermolecular attractive forces, Coulombic attractive forces. And so that's what these Maxwell-Boltzmann distribution curves represent, right? As we increase temperature, say from T1 to T2, so again, temperature 2 is greater than T1, what we find is that kinetic energy, the average kinetic energy, shifts over to the right. And subsequently, if this marking right here represents the amount of kinetic energy necessary to make that transition from the liquid to the gaseous state, we find that there is a significantly larger percentage of these molecules at temperature 2 that are able to transition. Okay, so again, increased temperature implies that we're going to see a faster rate of evaporization or vaporization. Okay. When we go to quantify this amount of energy, we can actually do so with the term molar heat of vaporization or the enthalpy of vaporization. Both kind of get it done. So the energy required to vaporize 1 mole of a liquid is known as the molar heat of vaporization. Okay, or again, what we might refer to as the enthalpy of vaporization. And again, you may remember vaporization. Got a little sloppy there, sorry guys. You might remember delta H from our thermodynamics unit, in a previous chemistry course. We will get back to thermo in second semester. So again, if we're representing this, this physical process out to go from the liquid to the gaseous state, there is a requirement of energy. So we would consider it to be a reactant. As far as our potential energy diagram goes, in going from the liquid to the gaseous state, we represent this as an increase, and therefore we have a positive denoting the endothermic nature of this process. Okay, so we're going to talk about what it means, to vaporize, as far as what is happening on the molecular level. Okay, well, initially what we find is molecules are moving from the liquid to the empty space. If we are in some confined or closed container, and a vapor phase is ultimately established. So over time, we're going to see that the liquid is transitioning to the gaseous state, vaporizing, evaporating, and we see a buildup of gaseous molecules. Subsequently, what happens is we find that over time, the concentration of molecules in that vapor phase obviously increases, right? Now, once we have enough moles of gaseous molecules, these are going to start to condense. And so this process is going to run in reverse, essentially, where now these gaseous molecules have the opportunity to strike the surface of that liquid. They'll become trapped by the intermolecular forces, and that's how that condensation is going to take place. Okay. Now, for any given temperature, the rate of evaporation is constant. Okay. But once this process begins, ultimately, as we increase the concentration of the molecules in the vapor phase, the rate of condensation is going to start increasing. Okay. Again, rate is concentration dependent in this case. Eventually what happens is that the rate of evaporization is going to become equal to the rate of condensation. Okay, the forward direction of this process is going to equal to the reverse direction as far as rate goes. And we call this a state of dynamic equilibrium. The pressure that exists at this state of dynamic equilibrium, that's what we call our equilibrium vapor pressure. Okay, so if ever we're talking about equilibrium vapor pressure, that means that we've reached this state of equilibrium. Rate of condensation is equal to the rate of evaporation. And whatever the pressure is at that moment, that is the vapor pressure. So more often than not, we normally don't even call it the equilibrium vapor pressure. We normally just refer to it as the vapor pressure. Okay, a couple quick considerations as far as a couple different scenarios. Let's say in scenario one, we have some liquid in a container and it is an open container. What we're going to see happen is that over time, these gas molecules are going to vaporize, right? But because it's an open container, they're going to leave that container. And so with enough time, we're going to see that these molecules completely vaporize. Okay, there will be no liquid remaining. If there's no liquid remaining at some point, then the rate of vaporization goes to zero. And so we can't have a state of equilibrium. So if we have an open container, we can't really talk about vapor pressure in this scenario. Okay, we only really talk about vapor pressure as far as a closed container goes. In this case, let's say we have an insufficient amount of the liquid. So let's say that this is super volatile. It's going to have a really, really high vapor pressure, and we haven't added actually that much liquid. Might have actually been more appropriate to have a line down here. And so all that liquid, vaporizes over time in a closed container. And so we have a buildup of molecules in the vapor phase. But even so, what we find is that we have too little concentration of that gas to recondense. And if that happens, if we're not seeing condensation take place, then going back to that equilibrium expression, we're not seeing the reverse direction take place. And so ultimately, we're going to say that there's no equilibrium, and this is because we are not fully saturated. You need to have a completely saturated airspace. You need to have that airspace with as many gas molecules as possible, such that the condensation process is taking place. Now, finally, this is kind of our perfect scenario here. We have a saturated airspace. We have plenty of volume of the liquid remaining. And so while we're seeing vaporization take place, we also see condensation taking place as well. So this is kind of our happy scenario. Now, in this scenario, it may look as though nothing is happening, but again, we are seeing vaporization, we're seeing condensation, maybe not macroscopically, but both of those things are occurring. But what we would expect is that we would see no change in the volume of the liquid, volume of L, or moles of gas. Okay, so we would not be able to observe those things. Those things do not change, though both processes, the forward and the reverse direction, are happening simultaneously. Okay. When it comes to vaporization, when it comes to vapor pressure, these things tie into boiling point. When it comes to boiling point, simple definition is going to be the temperature at which the vapor pressure of a liquid is equal to the external pressure. And so normally, if we are, say, boiling water or something, we're talking about an external pressure of about 1 atmosphere or 760 millimeters of mercury, right? That's kind of our standard kind of working pressure at normal kind of altitudes. So let's say we're studying gas X, okay? What we find is that 25 degrees Celsius, maybe this is its vapor pressure, okay? So if we had a closed container of the stuff, over time it vaporizes, and this is its equilibrium vapor pressure, 80 millimeters of mercury there. What we find, though, is that as we increase temperature, the vapor pressure increases. And so that's true for all liquids, right? As temperature increases, so does PVAP, or a way that we can abbreviate vapor pressure. So it's a trend, right? We're going to give this system more kinetic energy. More of it's going to transition from the liquid to the gaseous state. Now at 90 degrees, what we find is that the vapor pressure actually equals 760 millimeters of mercury. And so this right here for molecule X, whatever that may be, is actually going to be its boiling point, because at 90 degrees Celsius, it has reached a vapor pressure that would be equal, assuming we're running this, maybe in our classroom, of the external pressure. And so the way that, boiling actually works is that as these liquid molecules within some sample start to gain sufficient energy, obviously it's going to vaporize, and not just necessarily at the surface, but within the sample itself. And so we get these bubbles to form, right? You can imagine, some beaker on a hot plate, and we see these bubbles, start to just, rip from the bottom of the beaker, where we're seeing probably the hottest temperatures given the proximity to the hot plate. So bubbles start to form. Right now in these bubbles, we are going to see, let's just talk about water in this case. We're going to see gaseous water molecules, okay? And those things are getting hotter and hotter and hotter. And pressure is going to build within that bubble, okay? Now, pressure exerted on that bubble is because of two things. One, it's because of atmospheric pressure. So if the beaker's open, you just have atmospheric pressure kind of pushing down on it. And that bubble's also going to experience some hydrostatic pressure, which is basically just the pressure of the water in the sample above it, right? Pushing down on it. Imagine being at the bottom of a pool and feeling that pressure. Okay, so bubbles are starting to form. They're starting to be subjected to mostly external atmospheric pressure with a little bit of hydrostatic pressure. So again, we have that pressure inside of the bubble, and that's due just to the vapor pressure. Eventually what happens is, as that pressure inside that bubble, okay, as that vapor pressure in essentially what is a closed container, it becomes equal to the external pressure, the bubble is going to rise to the surface and burst. And that's what we visually observe, right? So, and I'm sure you have probably experience with this or are familiar with this phenomena, but boiling point is dependent on external pressure, okay? So for water, for instance, we know the boiling point is about 100 degrees Celsius at 1 atmosphere. However, the boiling point for water is actually less at, say, like 0.5 atmosphere. It's only 82 degrees Celsius. The idea being is that you, like, at 82 degrees, your vapor pressure for water is going to be 0.5 atmosphere. And that's all you need to do. Once that vapor pressure matches the external pressure, that's that moment rather, that we shift from just kind of vaporization to boiling at that point. Okay, so you might be wondering, how do intermolecular forces kind of play a role in this? And again, I think you probably could guess. The stronger the intermolecular forces are, it has some ramifications. The first is that if you're a molecule and you have really strong intermolecular forces, which means you stick to your neighboring molecules really, really well, you're going to have a really low vapor pressure, right? You are going to tend to stay in the liquid state. Okay? And again, if you have these really strong intermolecular forces, you're going to have a high boiling point and a high enthalpy of vaporization, or HVAP, because you require a lot of energy to go from the liquid to the gaseous state. Okay, so the stronger the intermolecular forces, we see three kind of trends, right? We'd expect those liquids to have really, really low vaporization vapor pressures, and it would require a lot of energy to go from that liquid to the gaseous state. Subsequently, we'd have to really get that thing kind of cranking on a hot plate or over a Bunsen burner in order to get it to boil. Okay. And again, that's just kind of what I've alluded to here. It takes a lot of energy to overcome these intermolecular forces. And I think it's worth a discussion to talk about what I mean truly by saying overcome intermolecular forces. If you're talking about melting something, so let's say we have a solid, which has a really, really closely compacted structure. When we transition to the liquid state, what we're going to notice about that liquid state is that these molecules are still really, really close together, right? The spatial arrangement. And so in going from solid to liquid, yes, absolutely, we are going to be, breaking some intermolecular forces, okay? But when we go from the liquid, say, to the gaseous state, at this point, it's not even about breaking, some of the intermolecular forces. We are really completely overcoming these intermolecular forces. We are completely separating out these molecules, right? Like, per the ideal gas law and kind of its tenets, we're assuming that no intermolecular forces actually exist between these gaseous molecules. They're that far apart, respectively, compared to liquids and certainly solids, okay? So that's why it takes a lot of energy in going from a liquid to a gas, because you are completely separating those molecules out. You are completely overcoming the intermolecular forces. Okay? All right, so we'll try to put this into play. Let's say we have the following question. Okay, so given the following data, which molecule has the stronger intermolecular forces? Justify your answer. And so it's kind of a strategy. RTQ, ATQ. Let's read the question. Let's answer the question. So given the following data, we have to make sure that we are making reference to data. We have to address which one we believe, given the data, has stronger intermolecular forces, and ultimately our answer has to have some sort of justification. So we're given the following molecules and their respective boiling points. So for benzene, we see the boiling point is 80.1. For ethanol, we see it is 78.3, degrees Celsius for both. So based off of boiling points alone, what this, says to me is that given that benzene has a slightly higher boiling point, it requires more energy to go from that liquid to the gaseous state. And subsequently, I would go with benzene having having stronger intermolecular forces. So let's break this down. The first thing I want to do is to address, I don't even know if I'm going to spell this right, address. There might be one D. Maybe there's one S. In either case, we are going to address each molecule separately. Okay, so based on what we see with these molecules, we want to determine what are the intermolecular forces in play. Well, when I take a look at benzene, all I see is carbon-carbon and carbon-hydrogen bonds, okay? We know both of those are nonpolar, carbon-carbon in particular, and even that carbon-hydrogen bond, the electronegativity difference, we're going to assume to be negligible, and we consider carbon-hydrogen bonds to be effectively nonpolar. So, given the presence of only nonpolar bonds, we find that it is a nonpolar molecule, and therefore experiences only London dispersion forces, which traditionally are rather weak. If we take a look at ethanol, ethanol is a little bit different. We have the OH group, the hydroxyl group, as far as like the ethanol goes, what makes it an alcohol. And this moiety, this functional group, allows it to experience hydrogen bonding with neighboring ethanol molecules. And so not only is it a polar molecule, given the presence of the asymmetry and the fact that we have the really electronegative oxygen, the polar molecule, obviously, it's going to have London dispersion forces, as all molecules do. It's going to have dipole-dipole forces, given the polarity, but it also has this hydrogen bonding capabilities. So this is interesting to me. Given these boiling points and given what I know to be true about these molecules, I'm looking at an ethanol molecule that has really, really strong IMFs, yet it actually has a lower boiling point. Okay, so now becomes the justification. How can I remedy essentially this, discrepancy? So, given that benzene, so this is my answer, right? This is me actually answering the question, that ATQ part here. Given that benzene has a slightly higher boiling point, it is suggestive, and we'll come back to this word, that it has stronger IMFs, given that more kinetic energy is needed to overcome them, right? As we transition from the liquid to the gaseous state, okay? So that's my answer, right? Slightly higher boiling point, that's the why I believe it has stronger IMFs. So how do we, again, remedy this? Well, in looking at benzene, it has a larger electron cloud, right? There's more atoms present. There's more electrons present. It has this larger electron cloud. And not only does it have a larger electron cloud, it also has the possibility of resonance, right? It has those pi bonds that are delocalized, which means those electrons are constantly in motion. And as a result of having a larger electron cloud and having these delocalized, pi bonds, what we find is that this is going to make that benzene molecule highly polarizable. And if you remember, that's kind of the key word, right? Highly polarizable. If a molecule is highly polarizable and it's nonpolar, what that does is that really increases the strength of the London dispersion forces. So much so in this scenario that benzene actually has intermolecular forces comparable, or perhaps, as we're suggesting, even greater than the ethanol in terms of its dipole-dipole and its hydrogen bonds. Okay, so that's my answer, right? We're going to go with benzene that has a higher boiling point, and the why is because the strength of its London dispersion forces, given its increased polarizability because of the delocalized pi bonds, because of the larger electron cloud, it just has stronger IMFs. That must be the why. And so that would be kind of your final answer. Now, the reason I've chosen this question is because of kind of a type moment, in the sense that we were given boiling point data. But oddly enough, had we been given, say, enthalpy of vaporization values or PVAP values, what we would find is that ETOH, which is another way to kind of shorthand ethanol, actually has a higher delta H vaporization and a lower PVAP at 25 degrees Celsius than benzene. Okay, so given the data that we were presented with, that would have been like the perfect answer, right? We have the justification, we're talking about the strength of those dispersion forces, given the polarizability of benzene. But had we been given different data, we might have actually come up with a different answer. All right, thanks for tuning in, guys. All right, bye.